Evident 1222 information.
1222, go ahead.
Evident 1222 checking location. This 1050 is at Hicks and Gray Road, is that correct?
1222 Effingham, 10-4, that is what the caller advised.
22, 10-4. Evident 1222.
1222, go ahead.
Evident 1222, I'll be 1023, this 1050. Looks like we might possibly have fire, I guess the smoke. Appears we got one victim down on the road, possibly one in the car. I'll be needing some assistance. What's the ETA on fire and ambulance?
1222 Effingham, 10-4. Kinmundy Alma Fire Department advises ETA 5 minutes, ambulance 5 to 7 minutes.
2210-4, advise ambulance and EMS to expedite. I'll be out of the car checking victims.
1222 10-4. 1261 Effingham, 1020.
Hey, 1261. I'm at Route 51, just north of Vernon.
Buddy, hey, buddy.
1025 with 1222 at Hicks and Gray Road.
We got
to assist with 1055.
All fire out.
Information. Twelve 22 status. 1261, 1222 is not answering. District Club unit is not answering status check on.
Binder of Tanner Industries Incorporated in Southampton, Pennsylvania, will present the Anhydrous Ammonia Properties section. David is the Director of Quality, Safety, and Regulatory Affairs and heads up the Ammonia Safety and Emergency Response Training Program known as ACERT. He also speaks and presents at numerous federal, state, and industry association conferences. He is very involved in leadership positions with various associations, national standards, and public sector organizations, such as chairing the Philadelphia LEPC. He serves on the National Transcare Task Group and has chaired the committee putting this ammonia program together.
We're going to talk today about some of the physical and chemical properties of anhydrous ammonia. And we've got four pretty short objectives, a lot of information going to be relayed, but four short objectives with this session today. One is, we want to give you the knowledge and understanding of the physical and chemical properties of anhydrous ammonia. And not just from the textbook side, but also how it relates to real life and real life incidents and scenarios. We also want to give you knowledge and understanding of health effects. How can people be harmed by exposures to anhydrous ammonia? And then what goes, the next objective, which goes hand in hand with that, is if we are dealing with a victim who's been exposed, how to at least give that initial first aid. Some do's and don'ts on first aid. And then the last objective in bringing this all together is as we understand the properties of anhydrous ammonia, using that knowledge to make sound risk-based response decisions and response recommendations based on that knowledge. All right, our agenda for today, we're going to look at some uses of anhydrous ammonia. One is it gives you a flavor on where you might encounter it, what type of industries utilize that chemical, but also it illustrates some properties of ammonia if we understand how it's used. And that's going to be short. We're not going to get in a lot of detail on that. We're going to get into more detail, though, on those physical and chemical properties. If we understand how this tiger in the tank operates by the book, and if we understand how it can act if it's getting out, especially if it's getting out and we don't want it to get out, we're going to be better prepared in dealing with potential incidents. And then health effects, primarily looking at inhalation, because do you think, is ammonia going to be considered a potential inhalation hazard? You can say yes. Yes. Yes, obviously. But primarily inhalation and skin exposure. We'll concentrate on that, initial first aid, and then bringing it all together at the back end and looking at, based on property data, property knowledge, how's that going to impact our response recommendations, do's and don'ts. So, we're talking about anhydrous ammonia, that liquefied compressed gas. This is 100% pure ammonia. Chemical formula for anhydrous ammonia is NH3, right? So it's 1 part nitrogen and 3 parts hydrogen. The word anhydrous, it means without water. So it's the pure stuff, liquefied compressed gas. Now, first thing I want to talk about, though, before we get into the session material, is there's a difference between anhydrous ammonia and what's commonly called aqua ammonia, or ammonium hydroxide. And this gets into clear communication, understanding what you are dealing with. I've been involved with some real incidents. I do a lot of live release exercises throughout the year. I've been in a lot of drills, simulated exercises. And probably almost any exercise I've been involved with, at the end of the day, when you have that debriefing or hot wash, probably communication comes up, right? Something wasn't understood. I didn't quite understand what you meant by that. So first is, I just want to remind you that there's a difference between anhydrous ammonia and aqua ammonia. Anhydrous ammonia, liquefied compressed gas, 100%. Aqua ammonia, also called ammonium hydroxide, the DOT, Department of Transportation, its proper shipping name is ammonia solutions, right? That's an ammonia and water mixture. It could be in any concentration of 10 to 35% ammonia concentration. Most commonly you see out there is a 19% aqua ammonia solution is very popular, or 30% concentration are the most popular. But if we're responding to an incident and we've got a leak. It's a container. Maybe it's over the road, over the rail. Maybe it's at a fixed facility. And you roll and they say, well, our ammonia tank is leaking. You want to make sure you understand, are you dealing with anhydrous ammonia or aqua ammonia? Both are hazardous. Obviously, anhydrous is going to be more hazardous as a liquefied compressed gas. So let's look at some ammonia uses. What's the #1 use of ammonia in this country? Fertilizer, right? It's the first one up there. Why? What property of ammonia makes it a good fertilizer? Nitrogen content. By molecular weight, it's 82% nitrogen. Now, think about it though. If I put pure anhydrous ammonia on live crop, what would it do? It would burn it. Why? What property, what's the property behind that? Well, it's nitrogen, but not just nitrogen. What type of material is ammonia? Is it corrosive? Yeah, absolutely. So farmers use it pre-planting, post-planting to get that nitrogen load for crop production. Some other uses, power plants. They can use either anhydrous ammonia or aqua ammonia. So here's where that clear communication can come into play. But especially coal-fired plants or even natural gas-fired plants, when they make electricity and they burn that stuff, they'll generate what's called NOx, nitrous oxide emissions. And they're harmful air pollutants. A good scrubber for the NOx, to knock down the NOx, is ammonia. Industrial refrigeration. You know, not your small supermarket stores, but cold storage warehouses, public cold storage warehouses, those type of folks. They use anhydrous ammonia. Why? What property of ammonia makes it a good refrigerant?
It absorbs the energy.
It absorbs heat, right? Absorbs energy, but it absorbs a lot of heat. When ammonia boils, we're going to talk about this on the next slide, but when ammonia boils, it absorbs a tremendous amount of heat. That's going to come back into play when we look at exposures, and we look at pressure-temperature relationships, and we look at dealing with ammonia, that high absorbance of heat. The heat treat industry will use ammonia. They'll usually crack it back to nitrogen and hydrogen to treat metals or parts or keep them aesthetically pleasing, nice and shiny, moisture-free atmospheres. Water treatment. Not every water treatment facility depends on some of their levels when they chlorinate water, but they could use ammonia, either anhydrous or aqua. And what's dying out is in the old blueprint industry, they had the diazo process. I don't know if anyone's old enough to remember smelling old blueprints rolling off. They had ammonia odor coming off of them, and that's pretty much being phased out. And there's other uses. This is not an all-encompassing list, just a quick hit. Pharmaceutical application, petrochemical, and then you also have the illicit use. People are stealing ammonia to make methamphetamine. And it's been a plague, it's been a challenge to the response community, to law enforcement. The meth makers, they need the liquid phase ammonia. And sometimes they steal containers. They'll steal cylinders or non-bulk containers. But a lot of times they'll put it in non-spec containers, igloo coolers, household propane tanks. And your size up in that hazmat recognition identification becomes very challenging when you're dealing with those type of situations. So just keep that in mind. There's also the illicit use. All right, if you could see inside an anhydrous ammonia rail car, storage tank, cargo trailer, it would look like water in a bottle. Obviously, it would not be in a plastic bottle like you have here. But if you had X-ray vision, it's colorless. It looks just like plain water. It has a pungent odor, right? It stinks. Ammonia has a low odor threshold. Does anyone know how many parts per million in air can an average person first detect ammonia vapor? Does anyone know that number?
2 parts?
Yeah, 2. 2 to 5. 2 to 5 parts per million. Federal OSHA says the permissible exposure limit is 50 parts per million. The recommended is 25. But so 2 to 5 is a lot less than those time-weighted average numbers on what someone will be allowed to work in all day. So think about it. Any chemical, when it has a low odor threshold, what's good about that?
Is it easy to get a problem?
Easy to detect. Good early warning. Ammonia is not going to sneak up on you. Right, think about it. Natural gas, pure state, any odor? No, they add that derivative, right? They have to odorize it, so yeah, we know we got a gas leak. Ammonia has it naturally. It has a low odor threshold, so there's good early warning. Now, there's a downside to that. What's the downside? Think about from the general public point of view.
They call it for everything.
Yeah, good early warning, right? They go, man, I smelled some of that. You know, what's going to happen? Am I going to die? You know, those type of concerns. So, but I think the upside, the good early warning, far outweighs the downside. Now, when any chemical changes state from liquid phase to gas, if I say gas or vapor, it means the same thing for this program, that's the boiling point. So ammonia boils at minus 28 degrees Fahrenheit. So what runs through your brain as responders, if we're rolling up on a scene, we pull out an MSDS or technical information on that chemical, and we see a low boiling point with ammonia, minus 28 Fahrenheit. What runs through your brain? Yeah, probably I'm dealing with a gas. Now, in the other block where we talk about types of ammonia releases, not in this block, you can get pooling of liquid ammonia on the ground, even in 100-degree days. That can happen. All right, but that's what's running through my brain. I'm probably dealing with a vapor phase, and just by seeing that number, minus 28 Fahrenheit, what else kind of runs through your brain? Does it make you think cold? Right? Yeah, it makes you think cold. And that's the property. Why is ammonia used in industrial refrigeration? Well, by the textbook, you'll read in the thing, it'll say it has a high latent heat of vaporization. That's fancy words for saying when this stuff boils, it absorbs a tremendous amount of heat to make things cold. Right? In physics, right, there's no such thing as cold. Right? It's the absence of heat that makes things cold. And ammonia does that at a tremendous rate. So think now, from I'm jumping ahead a little bit, we're going to come back to this, but now if I had an exposure, I have a high absorbance of heat when it boils at minus 28, what type of burn do you think victims could get if they got a liquid hit? Freeze burn, frostbite exposure. Understanding that property is going to come back to play when we're looking at exposures. Liquid density, ballpark about 5 pounds per gallon. Now, if it's cold, if the material's colder, it's going to get more dense, it'll be a little heavier. If it warms up a little bit, it'll be less dense, it'll be a little lighter. But ballpark about 5 pounds per gallon. That can come into play, that knowledge, in dealing with that jargon gap sometimes between public sector and industry. Because some industries, especially industrial refrigeration, right, they talk pounds. How much ammonia you got? Oh, we got 10,000 pounds. We got 20,000 pounds. If you rolled up on a scene and I said, I think we released 1,000 pounds of ammonia, do you think, does someone from the public sector have a good comprehension on what that entails, the volume amount? No, probably not. It's got a comment, it must be a lot. It's a bad one, right? But if I said now, even though it's a liquefied compressed gas, and it's going to be boiling as it gets out, but I think we released a couple hundred gallons, you have a better handle on what you're dealing with. So that's where that knowledge can come in. And then vapor density. What's the purpose of vapor density or vapor-specific gravity numbers? What do they tell you about a chemical? It's in a vapor state. Yeah, it's going to go up or down. Right? Is it heavier than air or lighter than air? They're all based off of air. Air is 1. So if I have a number less than 1, that tells me at least by the book, it's lighter than air. By the book, anhydrous ammonia vapor density is about 0.6. So at least by the book, it tells you that it's lighter than air. If you are just book smart, that number can fool you. Because ammonia will not always just be lighter than air. What factors do you think can keep ammonia vapor hugging the ground? Humidity. So wet weather, moisture. Ammonia loves moisture. It's very moisture seeking. So humidity can do it. What else? Temperature. And temperature, cold temperature, can keep it to the ground. Here's the picture that you see is a live release exercise done in the Philadelphia area. And you see the ammonia coming out of that tank and almost going right for the ground, not going up and away, right? Does that picture look like a 0.6 vapor density chemical? Obviously not, right? No, it doesn't. So there's an example. Just being book smart, that number can fool you, and you guys were right on it. Wet weather, moist weather, foggy, misty morning, ammonia cloud can hug the ground. Cold temperatures can hug the ground. Here in this shot, you've got a fair weather day, 65, partly sunny, and you see that cloud pretty much going up and away. But look how that cloud models, though. It takes that V pattern, right? V as in victory, looks like an ice cream cone, right? Three-dimensional. And ammonia will take this V pattern, right? Whether it's going up in the air or whether it's hugging the ground. And what happens is the sideline of that V is exceptionally defined, where it's something or nothing. And this will happen whether you have a visible white cloud or if I have an invisible leak, right? Because if I had a leak just off the vapor side of a container or a vapor line of a transfer line, would I see a white cloud off the vapor line? No, probably not. It's going to be invisible. When ammonia boils, right, when it changes state from liquid to gas, that's where you get that visible white cloud. Now, one thing I want to point out in the previous picture as well as this picture, these are live agent release exercises, but they're drills. You see response. What are the entry team in that picture? What level of dress are they? B, bravo, right? They're level B. I'm not suggesting in real life. Real life, we have an uncontrolled ammonia leak. What level would hazmat responders probably be dressed out in? A, alpha, right. So these live agent, but they are training exercises and they're in an outdoor situation. Here you see, what type of weather do you think is going on in this picture? Damp, right. We got damp, probably misty rain. And I'm using this shot just to illustrate, we talked about on this V pattern, how ammonia can go. I said sometimes it's a narrow V, sometimes it's a little more wide. In this shot here, you see a wider fan, right? A wider V pattern. Typically, because there's no 100% in hazmat, right? Typically, usually, most of the time. So typically, when we have these wet weather conditions, we'll tend to get a wider V pattern. And you see that here in the picture. I got a wider V going on. Same thing here. I've got a misty, rainy day in this shot. The clouds coming out and just bouncing back down to the ground. We're going to talk about some pressure-temperature relationships with ammonia. Now, that sounds scientific, but it's going to be some basic knowledge, because this comes into play in transfer operations. It comes into play for facilities and maintenance operations. But understanding some of this information, it also comes into play in response. And the first thing we're going to talk about is that ammonia has a high volumetric expansion ratio. It's a lot of syllables, and compressed gases have high volumetric expansion ratios. And you just see that posted as a ratio. You'll see 400 to 1, 600 to 1. Ammonia is very high, 850 to 1. All right? Big deal. What does that mean to us when we're dealing with maybe an ammonia leak? That we say this material has a high volumetric expansion ratio. Yeah, a little bit's going to go a long way, right? If I have, it's a liquefied compressed gas, a little bit of liquid gets out, it boils. When ammonia boils, I get that white cloud, but that little bit of liquid is going to give me a whole bunch of volume of vapor, right, in a ratio of 850 to 1. So a little bit goes a long way. You saw this picture in a couple slides before this, and you're at a slight disadvantage because you don't have depth to you, but that's a 6'4" individual in that picture. Just a visible cloud in that picture there. How many gallons or pounds, however you want to do it, of ammonia is making that white cloud, that visible cloud? How much do you think? Yeah, someone said a gallon. Excellent guess. Probably about 2 gallons, right? About 10 pounds of ammonia. So that gives you that visual on a little bit goes a long way. A lot of people guess, wow, 100 gallons, 50 gallons because they see this huge cloud. But ammonia, as a liquefied compressed gas, high volumetric expansion ratio. The other thing with ammonia, has a high coefficient of expansion. Now that's fancy words for saying if I had a quantity in a container, cargo trailer, rail car, storage tank, in those containers I have a liquid phase, liquefied compressed gas, and I've got a vapor phase on top of that container. All those containers have two phases of product in them. So if the container's just sitting out there and now we have a change in temperature, it was real cool in the morning and it got real hot by the afternoon. Ammonia as a property is going to expand. It's going to become less dense and take up more space. As it gets colder, it's going to get more dense and shrink down a little bit. And ammonia does this at a great rate, this accordion thing, based on its temperature. Right? It's based on temperature. Because of that property, containers are only filled to about an 85% fill limit. It's actually 82 to 87.5, depending on the temperature when it's filled, but ballpark, about 85%. And the reason for that is to allow for this expansion and contraction. If I only fill it to 85%, and now it warms up and expands, do I still have some vapor space on top? Yes, hopefully. Yeah. Yes, I do, right? I'll still have that. But if I overfill the container, let's say I filled it to 95% liquid, only 5% vapor space, and now it warms up, what don't I have anymore? No head space. And now what type of pressure is on those containers? Not vapor pressure, but what? Liquid, hydrostatic pressure, and that can rupture containers or pipes. So here's a couple pictures. Now these are small, non-bulk anhydrous ammonia containers. This is a small baby cylinder. They call them cartridges. And this was a 2-pound cartridge that was most likely overfilled slightly. When it was filled, the ammonia temperature, the liquefied compressed gas that went to the cartridge was cold. It was shipped out, stuck in a closet, 70-degree office-type setting, high coefficient of expansion, and ripped open that cartridge. Key point here with non-bulk containers. This is a baby cylinder. This is a small one. But even the taller cylinders, the cylinders that hold 100 pounds or 150 pounds of ammonia, 20 or 30 gallons about, they're filled by weight, not by volume, of product. These containers, these non-bulk containers, typically do not have safety relief valve protection for overpressure because they're shipped around. So think about it, in a fire situation, I have heat impingement. Even if that container is filled properly, could I still get that levy? Absolutely. So they can be pretty, they'll go like rockets in the air or rockets along the ground when they split open. So keep in mind, non-bulk containers, cartridges, cylinders, typically do not have safety relief valves. The other thing to keep in mind as responders, right, with this high coefficient of expansion, right, I don't want to trap liquid ammonia in piping without pressure relief of some kind, hydrostatic relief or some other type of safety relief. So, unless we're sure we got a good liaison on that scene, don't be valve turners, willy-nilly type valve turners. Know what you're doing because you don't want to trap liquid ammonia with this high coefficient of expansion property. The other thing that comes into play with pressure-temperature relationship with anhydrous ammonia, well, actually two other things, not just one other thing. Two things. One is it's a direct relationship. And this part's the easy part to understand. And all that means is if I know the temperature of the product, the liquid phase, if I know the temperature of that product inside that container, rail car, cargo trailer, storage tank, whatever it might be, I'll know the vapor pressure being exerted. And the easy part to understand, as it warms up, I'm going to build up pressure. So on the slide, you have some selected references. Minus 28 Fahrenheit, boiling point, 0 gauge pressure. As I go from minus 28 to 100 degrees Fahrenheit, the vapor pressure being exerted is going to rise. Gets hot, build up pressure. That's easy to understand. What's unique with ammonia, and this comes into play in response situations, is that this pressure-temperature relationship is independent of the volume amount in a container. For example, I have two storage tanks. Say they're sitting out in the parking lot here, and one is 75% liquid full, and the other's 5% liquid full. And they're not leaking, we're not drawing off. They're just sitting out there. Let's say today's weather was 50 degrees outside. If we looked at the pressure gauge on the 75% full tank, what pressure would it be reading about? 74, 75, in that range. How about the 5% full tank? Same. Say, all right, well, big deal. Here's where it comes into play. Think about it. If I was responding on a scene, I've got a leak going on, and they say, well, the pressure on that container is 0 gauge pressure. You say, great, all leaked out, right? Does that mean the container's empty? No, right? Because the volume has no bearing on this relationship. And if I can, by it being a direct relationship, if I can control one, I can control the other. Because they go hand in hand. They have to. It's a property of the material. Now, what are some things you can look for? What are some things you can look for if I had a container, let's say some springtime conditions, and they say the container's at 0 gauge pressure, does not mean it's empty, right? We know that as a response standpoint. But what are some things I can look for even from a distance to kind of size that up? Frost line or sweat line. Right, if I see that and I have a container that's showing 0 gauge pressure, that cues me up. There's liquid phase of anhydrous ammonia in that container. It's not empty. So you look for a frost line or sweat line. What you have on this slide is the pH scale. Right? pH of 7 is neutral. As I go 7 to 0, stronger the acid. 7 to 14, stronger the base. Which side of the scale does ammonia fall on? Base. And it's an exceptionally strong base or alkali. All right, big deal. Where does that come into play, do you think? It comes into play in a few different things.
Human tissue?
Excuse me?
Human tissue.
Yeah, human tissue. Health effects, right? If it gets on my skin, now I have the potential for a severe chemical alkaline or chemical caustic burn. And ammonia goes typically, like most bases, where it becomes a spreader. Right? Ammonia is a moisture-seeking missile. It loves moisture. What's your body mostly made of? Water. Right? So it's going to love you, but in a bad way. Right? You don't want to be loved like that. So one is knowing that it's a strong base or strong alkali, tissue damage, chemical burn, chemical alkali type burn. Where else do you think it comes into play, knowing that ammonia is a strong base? The environmental harm. And so a little bit of ammonia will drastically change the pH of water. So if we're using water downwind to knock down an ammonia vapor cloud, we're making aqua ammonia, ammonium hydroxide. Still a chance that that's a significant base or alkali? Absolutely. So we want to protect storm drains, protect sewer drains, stop runoff. Life safety obviously is always number one. So it comes into play in health effects. It comes into play in environmental considerations. Obviously, basic chemistry, what you can mix it with and not mix it with. What's the classic with ammonia? Don't mix. They tell you this. Don't do this at home even. Don't mix ammonia what? Bleach, chlorine, right? A little Clorox bleach, a little ammonia-based cleaner. What do you get? Poof, right? Yeah, not a good thing. So knowing it's a strong base gets into reactivity with other type chemicals. And then the other thing, ammonia is corrosive to certain metals. So copper, brass, zinc alloys. It'll start to corrode it. And you'll see that a greenish corrosion type color in that picture there. That was a material of incompatibility that was used by a guy taking ammonia out of a cylinder. And he didn't know compatibility of metals with ammonia. And that fitting failed. He suffered inhalation exposure. He recovered, rushed to the hospital and recovered from that. But if you see a greenish corrosion color maybe on a valve, or if you're doing site inspections, that type of stuff, that's a material of incompatibility. It's not going to hold up. It doesn't go right away, but it's going to go. The next property we're going to talk about is flammability. Now, usually it's not up on the screen, but as responders, if we're researching the flammability of a material, what's usually the first data point that catches our eye? Well, flash point, right? Flash point. Like gasoline has a flash point. Anhydrous ammonia does not have a flash point. Then the next thing we look at is LEL, UEL, right? Lower explosive limit, upper explosive limit. And so now, and what's LEL, UEL based on? Mixing what in air? Ammonia vapor, right? It's based on a vapor concentration in air. So when you think of the big picture with LEL, UEL, the scale on that goes 0 to 100%. Right? I got none of the chemical vapor in air, or I have only that chemical and no air left. And as you cycle through, you need to add ignition, and finally at some point, woof, you get it to burn, you get it to explode. My LEL. Then I can continue to fire it off till I reach a point where the vapor concentration in air is too rich. And I just get click again, right? I can't get it to go. It's my UEL, upper explosive limit. So when you look at those data points, that's your window of flammability. That's when bad stuff can happen. Most references will put that LEL, UEL range for ammonia vapor at 16 to 25%. Just being book smart for a minute, that's a relatively high LEL and a relatively narrow range. Just think, you all might be calculator dependent, but how many parts per million is 16% in air? Anybody can do it without a calculator? 160,000. 160,000 parts per million. So that's a lot of stuff. The widest range you'll see in the NIOSH Pocket Guide, they list that LEL, UEL for ammonia vapor at 15 to 28%. Now, keep in mind, when you see these data points, and really for any chemical, but especially with ammonia, that data point, that's test data. Pure, dry gas, anhydrous ammonia, tested under laboratory conditions. Real life, when something bad happens, are we dealing with that pure chemical in the pure state? No. There could be other stuff in the mix. And we're certainly not dealing with laboratory type conditions. So here's how I judge it in real life. An outdoor ammonia leak, outside, I'm not super worried about flammability with anhydrous ammonia. Indoor leak, I am concerned about flammability. All right, because I can have, especially in industrial refrigeration, is where you've seen it from time to time. And in industrial refrigeration, unlike the other users of ammonia that we talked about, power plants, water treatment, heat treaters, those type of folks, they take ammonia, they use it up, they exhaust it. They got to get more ammonia. In industrial refrigeration, now that's fixed facility stuff, but that ammonia is going round and round. They're boiling it, condensing it, boiling it, condensing it. Just loops around. You've got pumps and compressors moving that product around. What type of contaminants do you think can get into the ammonia with that equipment? Oil. If I add some oil into my textbook LEL, UEL range, what do you think that does? Lowers it. Probably lowers my LEL and widens my range. So real life with flammability. Outdoor, I'm thinking about it. I'm not blowing it off, but I'm not super concerned about it outside. Indoor, that's where I'm very concerned about it. I'm not just judging it by the textbook data. I'm getting all my information in what I'm dealing with. With any chemical, there's dose response. Right? And most chemicals, not 100%, but most stuff, the greater the dose, the worse the response. Up to enough can kill people. Right? Fatal type concentrations. So what you have up on the screen there is a basic dose response chart for part per million concentrations of ammonia. And we've talked about some of this already. Very low odor threshold, right? 2 to 5 parts per million. We went through some of the worker limits. I kind of break it down into about 4 hurdles with dose response with ammonia. That first hurdle, look at doses, let's say 120, 130 parts per million. If I was dealing with a victim that was dosed at that level, that part per million value, what type of symptoms do you think that person might present with? So we've talked about some physical and chemical properties of ammonia, how this tiger in a tank acts by the book, but also how does that relate into some real life situations. And now, just very briefly, talk about bringing that data in, and where does that factor into play when we talk about response considerations. So I'm simple-minded, so I try to break things down very simply. And so I break it down into indoor-outdoor situations. Now, I could have a leak inside a building somewheres, and the ammonia's rolling out. That's also an outdoor leak. This is not just your leak source. This is where is the stuff. Is it contained inside or is it getting outside? Indoor, we just talked about it. I'm concerned with flammability. So when you think about that, ventilate, either positively or negatively. Positive pressure ventilation works better, but either is okay. Think about that ammonia irritation. It's very corrosive. It's going to burn skin. If I'm in bunker gear and SCBA, I'm a first-in company, am I going to be impervious to ammonia vapor? No. Right? So think about that, right? If you're sweating, you'll feel burning here. Groin area, under your armpits. So level of dress, thoughts, and consideration has to come into play. If I'm dealing with, that product's now getting out, it's outside, or it's an over-the-road cargo trailer incident or a rail car incident, my main concern that I'm thinking right away is my downwind threats. Right? And when you think about that, think about, do you see a white cloud? What part of the container or what part of the process is leaking? Is it coming off the liquid side or the vapor side? Is it visible white cloud or is it invisible? Factor in now with your basic recognition identification, your initial size up, but factor in now what type of ammonia release am I dealing with? And then I'm going to factor in the weather, because with the type of release and the weather, what am I trying to figure out? Where it's going, yeah, and what else? Is it going to sink or swim, right? Is it more likely to hug the ground for a greater distance, or is it more likely to go up and away? So when we're looking at response considerations based on properties, I break it down into indoor versus outdoor. Just for review, indoor is where we're more worried about flammability, potential ignition happening. Outdoor, it's the downwind threats. Who could be impacted by that cloud.
Hi, welcome to this month's edition of Hazmat IQ, Chemical of the Month. My name is Joe Gorman. I'm from Hazmat IQ. What I need you guys to do before we start is get your books out, get your charts out. We're going to just run through the process, just practicing using the system. Okay, so what we chose this month was we chose ammonia as this month's Chemical of the Month. It's one of those, we get probably more questions on how do you respond to ammonia than any other chemical. All right, so you got your charts out, you got your books out, and here we go. So here we go. This one we're doing a known chemical. So we're going to use the system. So what we'll do on a known chemical is, the first part, step one is your chemical above the line or below the line? And once we determine that, we'll do our size up. After we size up the chemical, we'll go to step number 2, which we verify using your NIOSH. After we size up, verify, step 3 is we're getting ready to go to work. We need you to build a meter cockpit. The cockpit's designed to protect you. choose the proper PPE based not only on the chemical, but also on the mission that you're going to be running. And then step 4 is, I'm entering the hot zone. I want to make sure that I'm safe. So dressed in proper PPE based on my mission, and also based on the hazards of the chemical, we'll enter the hot zone, and we'll use the meters to determine red light or green light. Okay, so we're going to start with step number 1. Step number 1 is, we got to determine, is ammonia above the line or below the line. So we're going to look at alphabetical list for the word ammonia. You'll see it's not there. So what that'll do, it takes us to the above the line size up. Remember what size up is. Size up is just a damn good guess on what we assume we're going to see based on the hazards of this chemical. So you guys can see what the above the line is. You'll notice on the top of that above the line SOP, it says that you can wear turnout gear, SCBA, MOP, level B, based upon your mission and based upon who you work for. Obviously, if you work for the fire department, you're going to have turnout gear and SCBA. MOP gear would be more for the military. Level B may be industry. So you'll see our size up there. It's based on above the line. Then if you look at the last bullet all the way at the bottom, it says to continue to chart number 3. Alright, so chart number 3, what that'll do, it'll kind of fine-tune. It'll fine-tune our size up. So let's start where we always start, in the flammable clue box in the upper left corner. There we look for any part of the word ammonia. And it's alphabetical for you. You go down, it's not ammonia. There's nothing there. So we'll go, that gives us, it's not a flammable based on carbon and hydrogen. So we're going to go next over to the right, and we'll look in the corrosive gas box for the word ammonia. Remember what this is. It says first name corrosive gas clue. It doesn't say first name corrosive gas fact. It says clue. So we look for the word ammonia there, and we see it there. It's in blue because ammonia is a base. Why is it important to know if it's an acid or a base when it's a gas like that? Because a great thing to know about corrosive gases that are bases, they're all flammable. So now we know that it's a corrosive gas, that's a base, that's flammable, and you see at the very bottom of that box, it says I will be responding to red 0. So we'll look here at red 0, we'll zoom in on it, you'll see that it says corrosive gas, it's flammable, toxic, and corrosive. Notice in the F and pH box, you got a yellow X because there could be fluorine based on that family. It has a blue X because there could be a base in that family, and it has a red X, meaning that there could be an acid. So don't think that because you're a red 0, you exhibit all 3 of those. Remember what this is. It's telling me based on this family, it could have one of those 3 hazards. We've already determined that ammonia is going to pH blue. We'll bring our temperature gun to measure any kind of reactions. Anytime you've got a corrosive gas, when you start mixing it with water, or you start diluting it with water, or else maybe mixing it with an acid or a base, changing the pH. When you change the pH, you will have increasing temperature. We'll bring our LEL meter to measure flammability, and then we'll bring our toxic meters kind of later on. After we take care of the mitigation part, we want to try to reoccupy. The PID will come into play then. Alright, so the next question becomes, what do I wear on ammonia? It's a corrosive gas, and we know that corrosive gases leads us down the level A path, but we also know that ammonia is a corrosive gas that is also flammable. So flammable turnout gear. We're gonna think level A for corrosive gases. So what do? We have both. Well, let's go to our NIOSH. We're gonna verify the facts that the size up, and then from there we'll make our determination on exact PPE based on our mission once we arrive. So we're gonna go to our NIOSH. We look up ammonia. So I'll give you a second to go to ammonia. And remember, what you're seeing on this chart over on the right side of it, you don't have that on your chart. This is kind of a cheat sheet for when you get to the book. When you get to the book, what that basically is if you look all the way to the right side of that chart, where it says book there's our kind of our cheat sheet for when you go to the NIOSH. When we get to our book, what I did is I kind of put that list of size up verification, but I also put where do you look for it. So as you'll see, like the first one, SLG, Number one thing I want to know about ammonia is we predicted it was a gas. I want to now verify that it's a gas. So we are always going to look at the physical description. Says gas. We know that it's a gas. That's correct. Now I want to know if it's explosive. So I'm going to go to my DOT guide. And remember, the explosive guides are 112, 113, 114. What you see in the DOT box is 125 for anhydrous, which means no water. Make it simple, it's a gas. And those other three are ammonia solutions, like the Windex to Super Windex. So there we know that it's not explosive. And also, while we're there, we can look at to determine if it's radioactive or not. Remember, our rad guides are 161 through 166. And as you can see, based on both solution and anhydrous, none of those are there. So we can cross out rad. Of course, still bringing our rad meter with us. The next thing I want to know, does this chemical polymerize? So from that DOT box, I'm looking for the 3-digit guide number ending in a P. So none of those end in a P, so we're going to cross out the hazard of polymerization. Next thing I want to know, hey, I'm still there. Let's see if it's a corrosive gas. Remember, corrosive gases are 118, 123, 124, 125. So if you look at it, is this a corrosive gas? 125. The answer is yes, it's a corrosive gas. Next, I want to know if there's fluorine in this formula. So I look up in the in the formula box for the letter F. Do you see an F there? No. No hazard of fluorine. Remember, bring all your meters. So we're still going to bring the fluorine paper with you, the F paper. Next thing, let's check out flammability. In the size up, we predicted that ammonia was flammable. Let's verify it. We look at flash point in our properties, chemical physical properties. So what's flash point say? Na. Hey man, I thought you said it was flammable. No. Flash points are, remember what that stands for. The temperature that a liquid becomes flammable. This is a gas, so it's telling you it's not applicable because it's a gas. We're going to have to go down to LEL now to determine if it's flammable. And you see there, it's got a number. 15 for the LEL, 28 for the UEL. This gas is flammable. And then look what it says under LEL. Note, although ammonia does not meet the DOT definition, it should be treated as one. Let me put that in English. No shit, it's flammable. So be careful with this corrosive gas that's also flammable. The reason DOT doesn't put it in there, they've kind of made their own definition for flammability, and it just happens to fall right outside of the LEL and UEL for ammonia. But remember, outside, ammonia flammability, not that big an issue. Inside, big issue. So be aware. One last thing about LEL of ammonia. Remember, I don't know how many people have been taught this, but don't bring your LEL meter into a corrosive gas. You might fry it. I want to ask that dude, hey, if I'm not supposed to bring an LEL meter in there, that means the meter is more important than me. So at Hazmat IQ, we recommend you always bring your LEL meter in. And if it happens to go into a super high concentration, or you're dumb enough to stick your meter right in front of a leaking cylinder, and the readout goes blank, in our world, that's a red light. If you can't measure LEL, you shouldn't be in that environment. So remember, bring your LEL meter. Next thing we want to know, where is this gas going? Well, the molecular weight is 17. Air is 29, so this is going down. So it's going to go down. Now I want to know if it's going to mix with water, because look, if this gas is lighter than air, but it absorbs water, it's going to take the weight of water and add it to the molecular weight of ammonia, and this possibility, you could have this gas going down. But as pure ammonia is solubility is about 34%, it's going to absorb water, so it will be sinking, but you're thinking, well, why is it sinking? Because it's got the water based on solubility. That's another thing to remember about solubility. If it absorbs water, we can bring a fog nozzle into there, spray the gas with a fog nozzle, have the spray be absorbed in the gas, and make ammonia into a solution. So put that in your toolbox and remember that, based on solubility. Any gas that's soluble at greater than 34%, we can use a fog nozzle to take that gas and make it into a solution. Next question. Let's see, can I use my PID? And the answer is, yes, I can bring my PID, because the IP is 10.18. So again, Another thing, that a misnomer out there, is we call the PID a volatile organic compound detector, VOC. Well, VOC, organic, means carbon and hydrogen, and we already looked at this formula, and it's got no carbon in it. It's got nitrogen and hydrogen, so don't get confused on this VOC thinking it's only for organic. This ammonia is an inorganic, and based on the IP, you can use the PID. All right, next question. Is there carbon and hydrogen in the formula? Because carbon and hydrogen will tell me that I can use my FID, the true organic vapor analyzer. So this one is inorganic, so it has no carbon and hydrogen, so you will not be able to pick it up with your FID. Next, we want to know, is this going to react in air or water? A couple of places we can look for that. Incompatibilities and reactivities, we're looking for the word water and air. It's not there. But remember, when chemicals are corrosive and you add water to them, they will change pH. It won't violently, this one will not violently react, but it will have increasing temperature. But based on what the book says, we're going to cross out water, we're going to cross out air, just be concerned with pH and water. Alright, so now we verified it. This is your call based on your emission. We know that now it is a corrosive gas that's flammable. If it's a line of sight rescue and somebody's dressed in regular street clothes and you show up in turnout gear and breathing apparatus and it's going to take you 10 minutes to get into a level A, you got to make a quick in, quick out decision wearing turnout gear and your breathing apparatus based on that person being alive, quick in, quick out operation. So we'll make a rescue in turnout gear and breathing apparatus, but when it comes to the plumbing part, now we want to fix the leak. Now what do we want to wear? Well, if I wear a level A to protect me from the corrosivity, I got to be super concerned with flammability. So you choose level A, no problem. But remember what the chart says. If you're wearing plastic, our red lights for flammability is 1% of the LEL. So sure, you can wear level A, but as soon as your LEL meter gets to 1, you get out. Or, okay, well, what if I want to wear turnout gear, Joe? Okay, wear turnout gear. But what hazard am I not protected from in turnout gear? I'm not protected from corrosive gases. So what do I need to be concerned with when I'm in turnout gear? My pH paper on my mask. If my pH paper on my mask turns blue, I'm in the plumbing mode, and I'm wearing turnout gear, red light, get out, change the environment. Well, how do I change the environment? Well, based on solubility, I can change it by using water. I'll take a fog nozzle, I'll spray it. If I'm in level A, I'm concerned with my LEL meter. If I'm in turnout gear, I'm concerned with my pH paper. But I can continue to work in either one of those levels of PPE as long as I haven't reached one of my red lights. So that's what I want you guys to be concerned with, to be thinking about with ammonia. Either one will work, but remember, justify your PPE based on your mission and justify your PPE based on meter readings. Let me just talk for a second about flammability. This one happened, this incident happened here in Houston. I think it was a Sunday morning. Ed Halka, a good buddy of mine from Houston Fire, told me about this. It was a Sunday morning. They had an inside gas leak at the Borden's ice cream plant where they used ammonia for a refrigerant. Strong odor of ammonia when they reached outside the building. They spoke with a gentleman who worked at the plant, and he said, yep, massive leak in the back corner. I'll show you where the valve is. He said, but I can't walk in there because my throat will be burning. So the guys at Houston Fire Department said, well, let's train you in real quick how to use breathing apparatus. Well, they taught him in a second how to wear his mask. They started walking down the street in front of that building, and the guy didn't feel comfortable. He said, I don't like the way this feels on my face. He backed out. As they were walking back to the command post, that's what happened to this non-flammable gas ammonia. Blew up that building. So remember, this is a dangerous chemical, especially when it's inside. Here's a good example of solubility and what happens when ammonia absorbs moisture. And even though the molecular weight is 17, if you can look kind of to the left side of that sign, Pearl Beer, you'll see that cloud back there. We had a truck Houston had a truck roll off that bridge back there and leaked its content of anhydrous ammonia gas. Absorbed moisture, the moisture made it heavier than air, and you can see where it's set. The last thing I want to talk about today, a lot of the young guys in the fire department now, young guys and women, don't even know who this guy Percy Johnson is. Percy Johnson was a firefighter in Shreveport, Louisiana, where he responded on a ammonia gas leak. The gas leak was inside of a warehouse. Hours into the incident, the leak was out of a pipe about, we'll say, 14 feet off the ground where he couldn't reach it. So wearing level A, him and his partner went in there, and they wanted to use a forklift. The forklift was designed to lift these guys up so they could work on the leak. The forklift was powered by propane. Percy was on the forklift. When they turned the forklift on and tried to lift Percy up, ignited the ammonia gas, killed Percy on the scene. So please don't forget, let's not let history repeat itself. So remember, learn from what happened with Percy. Realize that ammonia is a flammable, corrosive gas. Protect yourself accordingly. Use the Hazmat IQ system and be safe out there. Alright, so thanks again for this month's Chemical of the Month. We'll be putting these things out monthly now, again. So I'll see you again next month. So for now, peace out.